Hi, Chris.
Hey, good
Nice
afternoon
to meet
or morning, depending on where you are.
you. It's afternoon for me. I'm in Switzerland. How
Nice.
about you?
Morning, Raleigh, North Carolina, south of DC, about 4 hours.
Perfect. Good morning then, and welcome. So I'm
Thank you.
Peter. I'm your chair today, which means my job is to make your life as pleasant as possible for the next few
Awesome.
hours.
Sounds good.
Um, and I think we can start with just checking the technicalities. So
Mhm.
if you have a PowerPoint, maybe just sharing
Yep.
it, and if you
Sure.
have video or audio, we can test that too.
No, don't need video or audio.
Perfect.
How's that look?
Yes, I see a theory of the mechanics of information.
Yep.
So that looks perfect.
Should I leave it up or take it down until we get started?
Both are fine. So I'll just briefly say, introduce us, or you. I guess your surname is pronounced Hazard. Is that
Yes. Uh-huh.
good? And then you have so you present, and then there's the group discussion, and Carl summarizes in the end.
Yeah,
Yes. So I mean, leave it up if you like this. No problem with that.
sure thing.
And then I'll just check. Um, so usually record this.
Yeah.
And
Hmm.
I forget if you asked for it to be not public or
No,
something
this
like
this can
this.
be public.
Good. So then once the meeting is over, we'll put it on our YouTube channel and I'll send you the link. Uh,
Sounds good.
so it can also be good to have as notes, potentially. Carl likes to
Yeah.
speak quickly when he knows it's recorded. Good.
And
Exciting.
my slides are free to share. I sent an earlier version of the slides. It's almost the same, but I've made some tweaks.
Perfect. Yes. And it varies a little bit how many people come for these
Mhm.
meetings. Sometimes it's few, sometimes it's more, depending on people's availabilities and so on. But Carl should be here within just a few minutes. All right. Do you have any questions or something like this? Otherwise, I think
No.
I'm through my very short list
Well,
as
actually,
usual.
one quick one. So I know this is a wide berth of backgrounds. Where, what are people's backgrounds on information theory usually? Can I assume at least a base understanding of information theory?
Probably a basic one. So I'm a modeler myself, but I'm not an information theorist specifically,
Hmm.
right? So most people here would be quite familiar with Bayesian inference and so on, which is related but not the same. Um,
Yeah. Okay.
yeah, yeah. And I mean, otherwise we can ask in the end or something like this.
Yeah.
And it's very exciting. So yes, I've been looking forward to today. Allow me to send a brief email while we wait for Carl, just because
Sounds good.
I have to tell someone something.
Mhm.
Oh. Good morning, everyone.
Hey, Ron, good to see you. And hey, Sungwoo, nice to see you too.
Hi, Peter.
Good to see you
It's been
both.
a yes. Where are you now, Sungwoo? It's been a little while since I.
Oh yeah, I'm here in Korea as well, so I'm also preparing for my graduation. And
Wonderful.
thank you.
In Seoul, right? Still.
Yeah, nearby
Yeah,
this.
yeah, yeah. So is it morning for you then, or evening maybe?
Now it's almost like 11
Okay.
p.m. So
Yeah, yeah. Nice that you're here. Hi, Emre. Hi, Arun.
hey,
Hello.
hello.
Yeah, good. And like I said, we'll just wait for Carl to show up, and then we'll start the meeting in a second. Ron, I don't think I know where you are based, actually.
I'm in Denver. Sorry, I'm waking up. I got my coffee. I had my nose stripped on when I turned on the camera. I'm in Denver. I moved here from the Bay, from San Francisco about 10 years ago, and we love it.
Perfect.
Yeah.
Wonderful. Haven't been myself yet. Only getting a sense of the US slowly, actually, as a naive European. That takes longer than I had hoped.
You said you're in Switzerland, right? So Denmark is like Switzerland if it was next to a vast plain.
Yeah, for sure. And I can see Carl is here. Hey, Carl.
Hi there.
So I think we're ready to start the meeting. Today, Chris Hazard will present on a theory of the mechanics of information. So as I understand, you base this in information theory, Chris, and that means that, so he asked me what he should expect that people knows about information theory. And I think it varies a little bit, but now you're all ready for that, at least. So I should be fine. And it's a pleasure having you here, Chris. So just to remind everyone, we'll do a presentation, usually about 40 minutes or so, with some wiggle room on that. And then there's group discussion, and Carl will summarize in the end. The stage is yours, Chris.
Thank you. Yeah, today I'll be talking about the summary of about 15 years of work on a pretty exciting topic. So the bottom line up front here is that we've come up with a set of math that allows us to do inference directly from the data without using a model in the middle, really. It can be adapted for virtually every form of machine learning. We're at or near state of the art for virtually everything. It's one underlying mathematical technique with no hyperparameters. And it's perfectly human understandable in every way throughout the inference, in the same way that, think about a physics or a civil engineering final exam. What are the units of measurement every step of the way? Did you get it right? We can do exactly that while getting at or near state of the art performance and results. And so I'm going to present the mathematical theory of all of this. Personally, I would love to push this towards some sort of a grand unified theory of information and inference and connect it with many of the other theories. But then specific for this group, I've got some thoughts at the end about, okay, if active inference and free energy are a top-down approach of how learners work and how are they trying to resolve information, this is almost a bottom-up approach to the same thing. Can we find a way to unify these and meet in the middle and make some exciting breakthroughs? And further, going back to the grand unified idea, is this a direction towards the physics of information? And I think and I hope so. The outline of what I'm going to talk about today is first I'm going to give some relevant machine learning concepts. I know this audience, some people know those very well, some don't, but I'm going to make some connections there. Then talk about our general learning as measuring approach, how it works, and then go into the mathematical fundamentals. Then I'll pop up to talk about what it means. What does it mean for reinforcement learning? What does it mean to discover missing information? Then how does this correspond to higher dimensions? As the dimensionality increases, how can we think about these spaces and what can we learn about it? And then relate it back to free energy minimization and active inference. So to begin with, if you ask, what is machine learning? What is AI? If you ask 10 people, you'll get 20 answers, maybe 11 answers. One of my favorite ways to define machine learning is programming with data. So if programming with data is what you're doing, what are the building blocks? We can show that you can build a Turing machine with nothing other than a simple instruction like subtract and branch if negative. So we can build these complicated systems out of very simple single parts. On the left here, we have if then. Look, basically, if it's less than some value, it's 0. If it's greater than some value, it's 1. And we use that a lot in machine learning. Gradient boosted random forest, decision trees, that's the building block. Pretty much everybody here is very familiar with neural networks and the artificial and the real. And those have a very similar slope. That there's ReLU, but there's many curvier variants, especially speaking to biologists. And there's another form of machine learning that is just as old as neural networks in terms of the artificial sense, dating back to the 1940s, something known as instance-based learning, IBL, or case-based reasoning, KNN, K nearest neighbors. They're all different overlapping terms that basically mean I want to find the data that is the most relevant, and I want to interpolate to find the expected value. It's very simple, very basic. A graduate student or even an undergrad with a little bit of machine learning can code it up in an hour or less, an LLM in maybe 10 minutes. But it's got a lot of power behind it. And throughout the history of machine learning, it's kind of come and gone. But we're going to focus more on this. But as you see, if we're building a system that can learn, all of these building blocks look a bit similar. Now, in machine learning, again, some primer for folks who are less familiar with this space. If we have some data on the left here, some nice two-dimensional data here, we want to come up with a model that represents that data. So the graph in the top middle here, we can pick a model that is low variance, but also high bias. So it's just, we're going to have a line going up to the right and down to the left. It's very simple, but it's not a great model. We're not going to get good performance out of it. Versus on the bottom, I can literally connect the dots. and have very low bias, but I have high variance because it's bouncing around all over the place. And typically we refer to that as overfitting versus underfitting on the top. So machine learning is all about developing that good model that gives that pattern, but also doesn't get confused by that uncertainty of all that data that goes around. So what our approach here, and there's a kind of a punchy title or idea of learning is measuring. So the goal is, like that k-nearest neighbors or IBL approach, let's find the data that we would be least surprised if we substituted as represented for the data we don't have. Then we just find either the expected value or the marginal distribution of what would come out of that. Seems very simple in practice, and it is, but historically it has not succeeded that well in machine learning because what is distance? What is similar? Those are hard questions. And due to the work that I've been doing in the past 15 years of my group and some lucky, fortunate circumstances of finding the ways that the math came together, we've been able to crack the nut on many of these problems. So the steps here are, let's compute the substitutability surprisal of relevant data elements. So again, if I were to say, I want to predict what somebody's income is or the trajectory of this ball, I want to find the data that I've seen or that I've experienced that are most representative and connect the dots. So what would I be least surprised of if I substituted this data for this other data? And again, surprisal is negative log of the probability. So if I could say these are, I think 99% of the time I could just flip them and I wouldn't care, that would be, negative log of that would be, it'd have a low surprisal. So I want to minimize that surprisal when I'm finding the data. Now, if I have surprisal and I add the surprisals together, so how surprised would I be if I met somebody who is 7 feet tall, moderately surprised, they're rare, but they exist, but then somebody who was really good at limbo and 7 feet tall, that would be pretty unusual because of the conjunction there. What we can do here is, just like you can multiply probabilities and do all the Bayesian inference on that, you can do Bayesian inference equivalence in surprisal space on the logarithm of them. So if we sum and we add together these surprisals, that's the same as a logical conjunction, an and. So what we're going to do is we're going to find the data that would be least surprising if we substituted, transform it to sum them in L1, find the probability of each particular value, and we find the expected value. Very straightforward. Another interesting thing that falls out of this is it's targetless. Anybody who's dealt with machine learning, you build a model to predict a thing. That maybe it's supervised learning. You build a model to find the anomalies. You build a model to predict this. You have 1,000 models to answer some basic questions. Versus if you have this framework, you can answer any one of those sorts of problems by inferring right from the data. You don't have to build a model per problem. For reinforcement learning, we can condition on what is our state, what is the data that is most relevant there, and then draw from that marginal distribution and open and close or amplify depending on how much exploration and exploitation you'd like. But if you don't know, you can set it to 1 and say, I'd like to be as surprised as I normally am. So if I'm a domain expert, I shouldn't be very surprised. But if I'm a newbie, if I've never encountered this before, I should draw from that marginal distribution. So we can also do the same thing with anomaly detection. We can say what data elements, groups of data elements, are the most surprising overall, stack rank them. And that's it. It's very straightforward. And basically any sort of distance measure where surprisal is distance. And we've got a proof in the paper that we put up recently that with some basic assumptions, surprisal works as a distance method mathematically. So you can substitute it perfectly. An interesting thing that falls out of this is what we often call the data is the model philosophy. Now, when I say that, people often are taken aback, like, wait a minute, that's not the model. But a model is always some sort of reduction of some underlying system. So what we're really doing in the real world is there's some system, we collect some data, whether I'm a brain, whether I'm a machine learning system, and then from that, we build a model that represents the data or that is built from that data, and then we infer from the model. If we can get rid of that extra model step, so if we think about the data itself, that's a reduction of the real world too. There's really 2 models being built. If we can skip this step, we might be able to infer a lot more about what's really going on as opposed to what's going in the model, which has inductive bias. And again, what does that mean for the science of information? So that's the general high-level overview of what we'll be talking about today. What does it look like? Well, if we do an inference here, we can not just get a prediction, as you can see by the purple dot with the the whiskers on it for the mean absolute value, but we can get the probability density function of that particular prediction, as well as the green points, which are the data records or data elements that were used to make this particular prediction. This is a MOID, mean orbital intersection distance of Earth. It's a NASA JPL data set. We can apply this to any sort of thing. Being able to drill into saying, well, these are the records, these are the counterfactuals, this is the probability distribution, really starts to change what we're able to do with machine learning, especially when these are grounded in the real data. Fundamentals, I'll speak a bit to the math here. At the end, I'll link to our very long form paper that goes into all the details on it. But I just want to give you some of the high level concepts of how this works. So first, imagine we have two values and we want to find the expected difference. So let's say we've got that person who's extremely tall. If we're measuring, their height, in the US we use inches. So let's say to a ½ inch is about right, or to a centimeter is about what we care about, because when you go to sleep and you lay in bed at night, your spine elongates a little bit. If you do hard impact sports, your spine might compress. So even your height might vary a bit during the day. There's some uncertainty there that is both epistemic, which we can resolve if we just knew more about the situation. I knew you just got up, so therefore I'd expect you to be this much taller, but you had a bad night's sleep. So all of that information can inform it, but there's also irreducible uncertainty, for example, from nonlinear dynamics. If you have a chaotic system, you can prove that unless you have complete information of everything, there is this level of uncertainty you cannot resolve. We basically don't care here, but the idea is there's some amount of uncertainty that we'll treat as the same for inference. Again, for human height, maybe it's a centimeter, maybe it's a ½ inch, maybe it's a little tighter than that. It may be domain specific, but we'll assume that there's that deviation, that uncertainty. And that deviation is at least as big as the measurement error. If I'm measuring something repeatedly and I come up with that uncertainty of measurement, but it's no bigger than, or should be no bigger than, the residual of a really good model. Best model that you can build should be able to predict it within a certain amount. It should be between those. So it's a form of uncertainty plus or minus in whatever units of measurement are there for that. Then, if we know that, okay, what's the uncertainty around that? There's something known as the Lukaszek-Kromovsky metric, which basically says, if I know two values and I know the probability density functions around them, I can find that expected difference. If two people report to be the same height, they're not the same height to the same Planck length. There's always going to be an expected distance or difference. And that this gives us that expected difference, knowing that uncertainty. We also use the Laplace distribution here because the Laplace is maximum entry, minimizes assumptions. It's more robust and it's more efficient to compute. So information theory says we can use either, but there's a lot to be gained from the Laplace distribution. If you're interested in that, Nassim Taleb has extensive work in that space about why he thinks we've gone in the wrong route going for the Gaussian distribution for a lot of machine learning. But you can basically flip it in and out. We've done experiments. The results are very similar regardless of what you use. So the next one is, if we know that uncertainty, how can we compute surprise? There's a notion of cumulative residual entropy that Rao and a few others put forth in 2004, which I think is utterly brilliant and, at least in the information theory, not as widely used as it should be. Continuous entropy in continuous spaces is a hard problem. You get negative entropies. It doesn't make a lot of sense. But if you say there's some uncertainty and basically treat it, instead of binning the data as you would a nominal distribution or whatever, a discrete distribution, we just say that there's some uncertainty and have a continuous set of bins, it's really elegant. What's the probability that something falls within this residual? If you use a long tail distribution like Laplace, as you can see in the second bullet there, the difference, the absolute value of the difference divided by that deviation is the information. It is a very, very simple thing to compute, very straightforward. And so if we want to combine all of that together to say, okay, we know there's some uncertainty, what's the expected distance? What's the surprisal of substitution? That formula on the bottom, it's a little bit gnarly. We've derived it, we show how we got to it. But if you look at it very closely, it's elegantly simple and very fast to compute. So this can tell us how surprising any data element is compared to any other. Then, if we take this and we say, okay, can we measure the influence the same way that you would SHAP? What features are predictive of other features? Well, we're going to look at the power set, all possible coalitions of features to resolve the prediction, to resolve the uncertainty. We can do that without the inductive bias, and we can find the uncertainties across the power sets of features as well. So these are big enhancements over the state of the art of machine learning for feature importance. So for example, inductive bias, where you say, here's 3 variables or 4 variables that are predicting a target. What's really predictive of them? If A and B are basically the same inputs, and we build a model, gradient boosted random forest model, we can see that it selected A, but B was redundant, so there was some induction that dropped B entirely out of the model, versus A and B are actually contributing about the same. These sorts of techniques capture that, so they don't have those inductive biases. And it matters in the real world because a lot of real world data has these inductive biases, like this Boston housing data set, where B is a percentage of neighbors who were Black. And you can see that you can build a model that says that wasn't used hardly at all, versus actually in the data, it was very informative of predicting. So inductive biases are kind of everywhere. The last bit here is talking about okay, so how do we find those uncertainties to begin with? And what's really beautiful here is that if we just try to predict things and say, how well did we predict? And we converge and iterate, those uncertainties seem to converge. There's some nuance in there, but there seems to be, for a given domain, a fundamental uncertainty around every data element. And if we find, as we resolve those uncertainties and we look at the matrix, think of a confusion matrix of all the things that predict all the other things. Where are the asymmetries? Those are entropy trails, and we can use those asymmetries of entropy to find causal results. How do we scale this? I'll talk only very briefly about this, but the idea is if you've got a bucket of data with a certain set of features, we can run millions of records and no problem, but how do you get to billions and trillions of records? One is hierarchical data sharding. So just like, and we'll talk about it a little bit later, you have that pyramidal structure of generalization. Let's take a set of data and say, this is representative. What is the core set? What's a subset of data that gives us 95% of the signal? Let's use those, break down, subset the data into other pieces, and then we can give it 80% correct, 90% correct answer at the top, or we can drill down to the lower layers. And by just saying what is predictive, what is informative, we can have very powerful results and figure out a small subset of data that gives good answers for almost everything. Now, don't just believe me here. These are some empirical results to show that we are at or near state of the art for virtually everything. I have a subset of some of our metrics here. Here's supervised learning. For classification, we're roughly on par, a little behind, XGBoost and LightGBM, which are at the top. We're ahead on regression. But if we've got some little research that shows that we should be able to get ahead on both and pull ahead further by computing the deviations with a little bit higher quality. With regard to anomaly detection, where these techniques are the lead on those, and sort of precision recall, area under the curve, and ROC area under the curve as well. And we've even got some more room to improve on those. And for causal discovery, even though we're not trying to build a causal model, we're just trying to figure out what are the causal relationships, where are the entropic signatures. We do very well, and we tend to do better on real-world data sets as opposed to manufactured ones. And this is a small subset of the available benchmarks for causal discovery, and there's a lot of synthetic ones. There's a boatload of synthetic ones. But in our experience in the commercial world, we seem to do much better on those real-world data sets with those real-world entropies. Another thing that falls out from this is missing information. So here's a very simple toy problem of a water reservoir where some volume is coming in at a certain rate. It fills it up. There's a level set point. We want to keep it around here, and a controller, and a lever controller or level controller that regulates and lets the water out. So we want to keep the water in this range for whatever purpose. There's volume flowing out. If we're only capturing the data of the level, the volume out, and the level set point, as you can see in the bottom left, we can see that there's a causal relationship between the level and the level set point. It's stronger, but we don't know which direction they're going, and there's a lot of uncertainty. There's the missing information ratio, which says here's the uncertainty that we see in the prediction. We can again measure that. Then we know that deviation. So what's that ratio? How much missing information is there? We can see that we should be able to predict all of these much better. And again, that deviation is calculated. I think I skipped over this before, using the answer. So if I already know the answer, as a proxy for all the features I don't have, which if it's encoded in the data, you can just, think through that and use that information. I could imagine maybe the brain has that too. I don't know. But using that answer just the way you would in a homework problem, looking at the back of the book and then going back and working backward and trying to figure out what is there, we can see that there's stuff we don't understand. If we add the features that have that high missing information, we look at the features around them and say, what relates to these potentially? If we add those to the data, we can now see when we add, the volume in, we can, and the controller, we can see that, okay, we've resolved those. Those are just as predictive. We can't get much more information about those, a little bit, but not much, versus go and find the missing information for these features that are unpredictable, even within everything that we know. And so for us, especially working in the commercial world, this has given us a lot of capabilities to go find what more can we use and come up with better predictions, to come up with better causal outcomes. If we take this entire system and think about it from a reinforcement learning perspective, okay, so if we know that all these uncertainties, what can we do with it? One idea that has been core to some of our work is what we call conviction, which is a surprisal ratio. It's the ratio of expected surprisal. How surprised do I expect to be compared to the observed surprisal? So if I expect an outcome and I'm, whoa, that was not what I expected to see, I can see that ratio being very low or very high if I'm confident of it. What's interesting here, again, is that one means that I'm right where I expect to be an average. So I'm a domain expert. I don't expect to be surprised on a problem I've done 1,000 times before, but I would expect to be surprised on an area that I'm not a domain expert. So it naturally changes its statistical aperture depending on where you are in the data. So if we say, let's sample from that marginal distribution to come up with an answer. If we know that uncertainty, I'll say, well, or an action, I should say. Let's perform an action in that space. Let's make a move in the game. Let's change the joystick just a little bit for some controller. I follow that marginal distribution. There's also the notion in reinforcement learning of a goal. What are you trying to accomplish? Are you trying to maximize your score? Are you trying to minimize the time to completion? Well, we can find, as we search among that data and condition among that data, we can find what elements, what data records have we had in the past that in this realm of similar state are of the best combination of goals, and then draw from that marginal distribution. Now, notice that we get this partly for free because all the features are measured in terms of surprisal. So I can say which goals have a least surprising outcome and just condition on that. Instead of having a separate policy or separate, different parts of a reinforcement learner that as you traditionally build, all of these things sort of fall out naturally if you just put that goal conditioning on there. And so reinforcement learning is just really combining those features over time. We'll have latent features like rates and lags and what have you, but we're able to come up with using the same set of principles, a reinforcement learner that are we achieving the absolute state of the art here? No, but we're able to solve, lots of reinforcement learning problems relatively efficiently without any change in learning rate. We just set that learning rate to 1, that conviction to 1, and it just generally resolves and figures out where does it need to explore to learn more and resolve that uncertainty, and where can it exploit, and it just works. Yes, you can do better, make it learn faster by tweaking that surprisal ratio, but it's very robust. Okay, if we take another step and say, what does this mean for creativity? Creativity is often defined as something that is novel and valuable. We also can mention complexity that comes into a role sometimes in creativity, but all of these things now are building blocks that we can put together concretely and scientifically. Relative novelty, we talked about the sort of types of conditioning you can do, on minimizing surprisal. So we're going to say over all of everything we know. Now it could just be, I only know my domain, or I've been trained on the internet, so I know a good swath of what humans know or have access to that. How novel is this given everything that I know? How complex is it compared to everything that I know? Again, looking at every data element individually. And then what is the relative value? And because we're able to define all of these things in uncertainty of prediction, we can say how surprising is this value given where I expected it to be. So it is a relative value. And now we have everything that is basically in information space from a creativity perspective. So this is something that we can measure, relative creativity, how relatively creative is a solution, but also dial it in or dial it up or down, dial it down. If we would like to produce a more creative solution, the same way we'd like to produce a more explorative output of a reinforcement learner, these sets of math go together pretty neatly. And now I'm going to transition this part of the talk into thinking, okay, there's what we've done, what we've built. How does this start to relate to thinking about higher dimensional spaces and data, and then eventually active inference? So creativity, here's a nice tight example, invention of the light bulb. Obviously, it's a multidimensional optimization problem here. There's the filament, there's the gas, there's all of the things that Edison and all of his competitors were playing with, but they really had three things they wanted to optimize: the brightness, the cost, and how long it lasts. Because you can have something that works great, it's super expensive, but only lasts a short amount of time. No one's going to buy it. There's not a market. So there's an optimization problem there. Now, thinking about higher dimensional spaces, there's this kissing spheres problem in geometry. It's a very basic problem that helps people think about what this means and how these relate. So imagine I've got four spheres, or I'm basically patterning out in every dimension spheres or hyperspheres. And I want to find if all those spheres touch at exactly one point, what is the largest sphere I can have in the middle? And in 2 dimensions, it's the square root of 2 minus 1 is its radius, assuming all these spheres have a radius of 1. In 3 dimensions, it's the square root of 3 minus 1. We can work forward and say, okay, as we go to higher dimensions, 9 dimensions, that radius is 4. At 64 dimensions, that radius is 14. Recall that the whole box is 4 by 4 by 4, however many times. So that means that this sphere in the center is sticking out in every different direction. This relates closely to something known as Lebesgue spaces or Minkowski distance. They're different, but they're related in their mathematical topology. Everyone's familiar with L1, where you've got that nice circle, L infinity, where you've got a square, L0, L1, where you've got Manhattan distance, you've got that diamond right there. But as we go to fractional Lebesgue spaces, we crank that parameter down. We start noticing it looks more and more like a star until it looks like a plus. As we go to that limit of 0, and we're basically multiplying all the features, we're finding the geometric mean, which is it's not really a norm from a mathematical perspective. So it's a pseudo-norm, quasi-norm, I think is the technical term, which is great. But one of the problems is if you get any 0, the whole thing becomes zeros. Well, as I mentioned before, we've got these deviations, so we never quite get a 0. We always assume there's some marginal, very small probability that something can happen, or maximum entropy. Now, this is the same as dealing with L1 in the log space. So what's really beautiful here is that as we get closer to these Lebesgue zero spaces, we actually go towards probability theory, which then can be reflected in L1. And these mathematics kind of unify. What's further, just more speculative here, but very interesting, is if you go watch some of the videos for a game, A Slower Speed of Light, some folks said, what if we could travel near the speed of light? Well, that's hard to reason with. What if the speed of light was only 3 or 5 meters per second? What would the world look like? And as you move through this world, you can see it's sort of the rack focus, everything distorts. And the same mathematics that underlie some of these fractional Lebesgue topologies are the same sorts of things that underlie relativity. It's no weird coincidence that Minkowski, back to this Minkowski distance, was Einstein's PhD advisor. There's some fundamental relationships here. There's also people sometimes talk about these topologies as being pointy as you go to fractional Lebesgue spaces. That's only from the outside. From the inside, it actually becomes curvier because you've got to go around these large spaces. And what does this mean when we start to think about optimization and making decisions? I'm sure some of you are familiar with the idea of a Pareto frontier, which is the set of considerations you should make among. Use a classic game example. Think about a racing game, Mario Kart. You've got a bunch of things to select from. Cars that here's an engine that has this acceleration, this top speed, this, all these different trade-offs. Well, if you've got an engine or a cart or whatever that is universally better in every dimension, you shouldn't even consider and waste time thinking about the one that's worse. Now, if one has a higher top speed, one has better acceleration, now you have a trade-off. And typically, we only want to focus decisioning on that Pareto frontier, the distinction, the decisions that are meaningful. So on this left graph, somebody's actually worked through Mario Kart 8 and figured out among a couple of dimensions what configurations can we entirely rule out, so that we only make a distinction and a decision among that frontier. Well, what happens is as we go to higher and higher dimensions, everything starts becoming in the Pareto frontier, so we can't make a decision. We have to cut it down. We have to generalize. There's some work that some of you are probably familiar with that I thought was awesome by Lynn Tegmark and Rolnick from 2017, which were looking at why does deep learning work so well? And in the appendix of the paper, this is not their main result, but I was very fascinated and motivated by this, is they asked, what if we flatten a neural network? What do we need to do to represent the same outcomes? And it turns out that it becomes exponential. You need to have all of the configurations memorized and then generalized on top of that. So instead of doing this extremely expensive computational burden, if we generalize into a pyramidal structure, we get good results. And it goes back to that Pareto frontier of what data is the most salient, how do we collapse it into a few things so we can make a decision and not have everything in the Pareto frontier and have decision fatigue, or not decision fatigue, have analysis paralysis, because if I choose this, which is a little better, I'm going to harm something else. So this underlying idea of regularization, of generalization, is universal. But my question here with our techniques are, what can we do to better understand the modules of a learner? So traditionally, if you build, let's say, some sort of a pyramidal structure for your deep neural network, you can kind of see the layers. Of course, on the left here are some examples of some image recognition here, but that's really hard to tell with all these small fine grains. However, if we bucketize these and say there is here's a set of data that is representative, that gives us 70–80% accuracy, it's a subset of features, and a human can understand and debug and say, here's what this module does. Okay. Now, if we want better results, we need to say, of this cluster, of the subset of data, let's now go down to another subset of sharded data that is more relevant, more topical, that has a different or similar, overlapping, but maybe different subset of features, and now introspect it. I can understand that. This is not unlike mixtures of experts and other sorts of things in LLMs. So part of my push and motivation for this is, can we come up with a data-driven equivalent of this that is able to help us introspect the data and understand how a learner should behave, but then also be able to build a learner directly from the data? Early in my academic career, I worked a bit in combinatorial optimization, specifically with market models and combinatorial auctions. So imagine you're trying to solve some optimization problem that is very computationally expensive. You can show that if you boil things to prices and break the optimization problem down into sub-markets where they can pass these values around, it is very similar, where you've got these bigger chunks of smaller problems, of decomposition of problems. And you can get within 8% of optimum most of the time, even though you have those decompositions, and everything is debuggable. So I keep thinking back to, can we make learners that a human can understand every step of the way and still scale them to the things that we have today? If I want to learn how a Boeing 787 works, I know that I could spend 6 years of my life understanding some particular niche of it and get a good idea of how that piece works. No human knows how the whole thing works, but I know that I could do that for everything, versus we can't do that for machine learning systems, and we're working on doing that for the brain. So perhaps these ideas can give us some insight here. For looking at what this equivalency might look like, let's look at a toy problem, the classic exclusive OR. If I have I only emit 1 or positive if the values are different. If they're the same, I emit 0. On the bottom left, or the left side here, is an optimal neural network of basically 5 nodes that can produce an XOR. And this is very well studied. Versus on the right is instance-based learning, where I need 4 data points at a minimum, and I can interpolate and find the expected value there. They're similarly operationally complex, but on the right, it's much easier for a human to understand. is there a way that we can link these two theories and then again back to active inference and the information theory? So before I wrap up, which looks like I almost spot on with regard to time, I want to open some questions here, and also invite folks to check out our long form technical report. We've got another iteration coming out in the next week or two. There's a few minor errata and some new results that we're putting out there before we submit it to peer review. But can we link these fields together, and what exciting things can we learn? So in machine learning, especially LLMs and in other areas, there's the notion of data distillation or model distillation. So I've got a really well-trained learner over billions, hundreds of billions of tokens. Can I make a small one that just extracts that knowledge out very fast? And there's a large practice and area of research around figuring that out. My question here is, can we do that with data as opposed to distillation and training weights? Can we come up with if we know that this is the data the learner is being exposed to, can we figure out a, not necessarily optimum, but a good subset of data that represents that entire domain and see, did the learner learn that? How well does it do in the subset? Or given a learner that's already learned a domain, can we extract a subset of data and distill that out in a way that is human understandable so that we can figure out what should be going on in the learner, given what we know from the data, and what actually is going on in the learner, given the distilled data, again, human interpretable. How and where does free energy minimization map to our concepts, our bottom-up concepts for reinforcement learning? I think they map pretty tightly. We've not done the work yet, but I'm happy to talk to people about collaborating on how we can make these things meet in the middle. Do our brains or LLMs have this concept of, maybe not LLMs, but other machine learning techniques have this analog of missing information? I know that I'm not being able to predict as much as I should here because I've worked through the answers in the back of the book. I have a mental model of how knowable this is, but I know that I don't know. Can I go and find that information? As this technique scales, what more can we understand about the automated hierarchical decomposition, and how well does that map to other learners? Especially given some of the recent work in the computational mechanics, looking at causal mechanisms and what they call as causal leakage between layers. For example, if you've got a baseball, we're throwing a baseball back and forth, there's a minor wind, I can predict to a very accurate degree that Newtonian mechanics of the ball, and there's nothing that a single air molecule can really do to influence that beyond a statistical degree. Just the same way that there's a Nash equilibrium in game theory where an individual agent can't disrupt things. So there's that clean separation of emergence in that domain versus oftentimes in life, there's not such a clean distinction. So for making efficient learners, does there need to be a tight coupling there? Can we break it apart, and how much optimality do we lose? Is it more like combinatorial auctions where we only lose 8% of optimal, or is it do we lose a bit more than that? And is that usable? Open question. How can we better map latent features in this space to neural networks? Think spectral analysis type things. Think about all of the 3D translation, scale, rotation type transformations. Can we make those map? I've got a lot of ideas on that. We've got some early experiments, but that's another open area. And then how can we improve on this to actually get state of the art on all tasks at once? It feels like from our work that there is a way to change these deviations a bit to get at state of the art for all of these. I know for the supervised example, there's a little tweak in how we compute deviations where we can jump way ahead of XGBoost and LightGBM in terms of classification, but it harms our results on regression and the other way around. Can we get them both at the same time so that we can find that there is a Bayesian best inference from the data, maximum entropy is assumed, and can we build that sort of a system? Of course, if you know that something is Newtonian mechanics, you'll always do better by using the formula, but just given the data with maximum entropy, can we come up with that optimum solution in a unified theory of data? So that was a lot of information, and I am 1 minute over, which I'm kind of proud of. Normally I go over a little more than that, but I'll open it up to Professor Friston and any questions.
Thank you, Chris, for a wonderful talk and very filled to the brim with complex and interesting things. As is the custom, we will just briefly unmute our microphones and give you a round of applause.
Well done, Chris.
Yes.
Thanks, David.
So now we have just a bit of time for discussion, questions, and comments from the audience. I already have one in the chat, so I'll keep an eye on the chat and moderate a bit. But I thought I might start with just one question to frame the discussion, because there are plenty of things of interest that if let loose, I would just start asking about. But I guess the question is a little bit what you think would be nice to discuss, or which angle to take here. And so one thing I can think of, for example, is of course to say where I think the things you've presented, as far as I understand them, touches on, is similar to, is different from the work I'm used to doing, we're used to doing in active inference. But it might be that there are other things that are more relevant to you. So that's maybe the primary question from my side.
Oh yeah, for me, I wear several hats, like several of you probably do. At Howso is a very mission-oriented but for-profit company where we're trying to solve the black box by producing this sort of technology, so you can really know how every decision is made. You can debug and edit. So, for example, we've had in our early days flying a drone, in a simulator, indoor-outdoor navigation. 5 to 10 minutes of training data, we could get it to navigate that quite well. But like in 5 to 10 minutes of training data, you made a mistake. Oops. And now it's flying off into space. And you say, well, what if I just oh, this is the data that I used to train, and hit the delete, bam, it goes right back on track. And so to me, there's a lot of responsibility around this. And so I'm thinking, we learned how birds and butterflies flew to build airplanes, but airplanes look nothing like that. But now we're trying to make it more like that. So can we learn the science of information as we move towards these futures? So I'm really interested in collaborations and ways to figure out that underlying math. The other hat that I wear is my academic side. I want to keep pushing towards that grand unified theory of information. So for me, I'm like, any sort of these questions are very relevant and fascinating. And even from a brain perspective, trying to learn how the brain works, we've made some huge strides in that direction. But can we figure out from a data perspective how that maps, so that we can both help inform what the brain is doing and learn better and build better machine learning, but also can we use that data to map back to the brain? So I'd say probably everything interests me out of this.
All right. Yeah, it is, by the way, a fascinating dance, right, between understanding a biological system that does the thing we want to do and finding ways to do it, that they talk to each other, both of them.
Yeah.
Okay. So then, before giving the stage to Ron, who has a question for you, I'll just have a brief comment. Then I have more stuff to come back to. I have a long list of notes here, probably far too long. So one thing is, of course, active inference comes originally from trying to model what the brain is doing. And so that puts the pressure much more on making the models, theoretically coherent, principled, and so on, and less on them being able to solve concrete real-world tasks. But there are people working in artificial intelligence with active inference who are less interested in biomimesis, or mimicking, the brain, and more interested in I presume some of the things your company would also try to be doing, right, to solve actual concrete tasks, make drones fly and so on. So I guess one question is to which degree you find the brain part of active inference relevant, because we can also focus a bit more on the AI part. I'm on the brain part myself, but I know vaguely what the AI people are doing out there too.
Yeah, I mean, I think that to me, if you're coming up with an optimal learner, these things are all approximations of some underlying theory. And if you look at some areas of machine learning, I think it was 2018, there's a field of machine learning called Gaussian process regression, which is basically adding together a bunch of Gaussian mixtures that produce a result. And then there's kernel methods, which say, given some kernel of computation, how do I blend the local data in a way that gives me a good result? There's a long form journal article, I forget the venue, where they show that these are equivalent. Like they're not just two different approximations. Here's exactly isomorphically how they relate. And my intuition is that in the long term, all of these are all forms of another. So can we find that ground truth, the physics of information, and show that the brain is approximating that neural networks are approximating that, and is there that core truth, that core physics? So that's kind of what I'm pursuing. So I think it's a yes and I think it's no coincidence that coming from trying to model brains and finding the free energy minimization, I think there's no coincidence that tends to mimic and mirror some of the work that I've been working on.
So do you think there's a Bayesian reinterpretation of the things you've shown us now? So I'm trained to read the brain as a Bayesian engine that uses Bayesian inference to perceive and to act. And the thought is that that might be a way to generalize many of the current theories, such as reinforcement learning. And so one question from that perspective to the things you showed now is, given that you have methods that work, and especially given that they live in an information theoretic space, which is, I suppose, kind of a sibling to the Bayesian inference world, do you think you could reread or rewrite those methods as Bayesian inference of some kind? So it might be implementationally a disadvantage for sure. But what do you think?
Absolutely. Not only is it possible, but yes, completely. If you look at my grandfather, who was an engineer many years ago, gave me a book of several books that were from the 1920s that he learned from, which 2/3 of the book was logarithm tables.
Right.
And it was like, okay, here's all the math we do, but let's use the log tables because it's so much more efficient for a human to do it. And there's no difference here. Working in log space, as I talked about in some of the previous slides, is the same. You get the same results. It's just we're working in the negative log. Instead of doing lots of logarithms and exponents, we're just doing additions, multiplications, and divisions, and an occasional e to the whatever. So it's much more computationally efficient, but you absolutely could rewrite everything in Bayesian.
Exciting. And by the way, many of the implementations of Bayesian inference I use as a modeler are also usually in log space because they're much nicer to work within. Okay, so one difference, of course, is that active inference is Bayesian. The information theoretic things you showed is not necessarily, but compatible with, I think. Another is the brain versus AI. A third difference is that, of course, what active inference brings to the table, instead of or in addition to classical Bayesian inference methods, is that it also treats action selection as a kind of Bayesian inference process. So that's why it can replace reinforcement learning. In the sense that the aim is not just to predict the world, but also to pick the actions that changes the world so that it becomes in a state that you want. And so that's my last question, but before I'll shut up for now. But
this is.
So do you think
this is an area where
mostly I just wanted to ask about the action aspect of the things you showed. So I think most of what you showed, for good reason, is on the I'm in my vocabulary perceptual side, learning to predict, to figure out what's going on, to categorize, to reduce, and so on. But do you think would it be easy to build a little thermostat using entirely these principles? Is there an action component to it? That's my last question. And then I see David Bray has a comment maybe after yours.
Yes. So we, in our nightly testing in our software, we are doing things like, cart poll and the like. So actually doing that in a feedback loop in real time with our software, doing online learning.
Yeah.
And so what the unification we haven't made yet, but I think may exist, or it's either exact or approximate, is showing that, let's say that you're starting from scratch. We assume maximum entry over all the features. If they're nice and continuous, is it 0 to 1, 0 to infinity, whatever. So we just generate some pure noise in step 0 where there's nothing in the learner. And from that, we get some sort of response. And what we're trying to do is we're trying to find what state. So we've collected some data. We're some ways into the learning process. We've collected some data. Here's the state, the data that has state that we would be least surprised if we flipped it with, if we substituted it.
Yeah.
And then of those, we want to find the ones that have the goals that we maximize the best, whether it's maximizing, minimizing, attempting to achieve a value. And neither of these are hard. Like we're not just like, SQL query, find the goals. We are finding a soft, like what is soft fuzzy state? What are soft fuzzy goals? So we're trying to minimize our surprise if the state or the outcome were substituted. But we're also drawing from a sample from that marginal distribution to say, if we just don't know if this is a very sparse piece of data, try something, be a little bit wider because of that aperture of the bandwidth of the marginal PDF will be wider. And then naturally, as you get more and more data, it resolves it. And so I think, knowing from an active inference perspective, you're trying to do very similar things. It's stated in a different way, right? You're trying to minimize your surprisal from what you observe, and you're also trying to maximize goals. I can't help but to think these are either the same or very tightly related.
That's what I was thinking when you showed this slide as well, that this is one of the main points of interaction, I think, specifically where it becomes active also.
Yeah, this one, and I think the creativity one as well.
Agreed. Yeah, so an active inference agent does Bayesian inference to figure out the environment, and then it has goals which are specified as priors, fixed priors, over the kinds of observations or states you expect. And then you pick actions that make those states the most likely, or that makes the observations as unsurprising as possible given those goal priors as your expectations, while also maximizing the expected change in beliefs when you get that information. So there's an information gathering part and a goal recruitment part. And I'm curious, and I'm not sure how the information gathering part fits your creativity part. So that's the exploration thing. I pick this action because then I expect these observations, which would change my mind this much. So it's not random exploration; it's targeted towards info gain. So that's very exciting. I can't off the top of my head. Maybe Carl can kind of link them directly and formally, but I share your intuition that they must be close at least.
Here's another piece of intuition on it. So the way that we're doing reinforcement learning is not so much trying to looking forward to look back. We're just purely looking forward to draw those distributions. But from the creativity perspective, in the missing information perspective, we are looking forward to look back. And so I think that maybe active inference isn't exactly like what we're doing with reinforcement learning, but it's close. Maybe they're just from the different sides. But I think if you start to put in the missing information and the creativity, we might be able to actually link those two. So maybe you have hypothetical states that you're trying to reason out and say, what would I have learned? The counterfactuals. Now, let me also add that counterfactuals are very easy to obtain in our system. So let's say that you've got the reinforcement learner, and you say, now I just don't want to care about goal. What states are the most similar? What states are the most similar but give the opposite goals, or the counterfactual goals? You can run that query very easily. And so if you had some higher order operation, like let's say here's the part of the learner that's learning the world, and another learner that's learning the strategy or policy. That other learner could introspect and have some sort of a loop there to hypothetically model out. We've done little experiments with that for some early projects. We've not built a lot of that out, but I think there's a lot to be done there.
Okay, very exciting. So before I eat more time, David, if your comment was specifically to this discussion, maybe you want to bring it now, and otherwise I'll take.
I was actually going to. So, first, good job, Chris. Two, to try and bridge with what you're proposing and what I know of Carl's work and others in active inference, I was going to toss in a third dimension, which is the work of James G. March on organizational learning and decision making. And so specifically, the idea that you think about the fitness of beliefs relative to the ability to predict what happens in the environment. And this gets to your point about a counterfactual too. If I don't do something, or if I do the opposite action, what happens? And then again, gets to the minimizing of surprise, which is if the action that I attempted to do results in a high degree of surprise relative to what actually did emerge in the environment, then my ideas are unfit and thus need to be updated again via Bayesian method. Anyway, I toss it out because I am at the altar of James G. March. He did his work in the 90s in cybernetics and decision-making organizations. I think that's a possible way to link the top-down. I see Carl and active inference's work as top-down. I see your work as more bottoms-up. And I think there's actually a convergence there.
Yeah. As a kind of cybernetic, I mean, you could view active inference, I suppose, as a fully Bayesian cybernetic.
Yeah, and especially if you think about it as that there are learners that have beliefs, and then they are acting on their beliefs, attempting to minimize surprise as to what happens if what they see is maximum surprise or a high degree of surprise, then clearly their beliefs about the external world were suboptimal because they were surprised.
Okay.
And even the deviations that I talked about, where I'm trying to predict, like going back to human height, or a centimeter or a half inch or whatever your uncertainty, where they're the same, we converge in this little tiny cybernetic world, this little nonlinear dynamics world, to figure out what those are. But if we did it at a more macro scale around the environment, given the data, what more can we learn and infer from it in our own learner's model before it goes out and does things?
Yeah. Exciting. Okay, so I read that mostly as a comment, right, David? So I'll let Ron
Yeah, it's
ask
more of
his
a comment. I
question.
mean,
But
it
good
was really
comment.
just to
So
get
very
reaction
welcome.
from Chris,
Just to
and I
make
don't know if Carl has thoughts. Yep, go ahead.
okay. So then I'll so Ron wrote, and I can read it aloud, Ron, or you can say it yourself if you prefer.
Oh,
But he's
I'm happy to. Yeah, first of all, Chris, thank you so much. Carl, great. Excited to hear from you again today. Um, yeah, so the XOR example, me coming from, I'm a mutt, right? I've been sandwiched in between data science teams, but I'm not academically trained especially in the math. So I'm probably the slowest one here in the group. Um, but what I like about the XOR is like, okay, immediately it's like intuitive, and now I can dive a little deeper, I hope. Um, and so, yeah, could you just maybe slow down, Chris, and just help me? I really want to understand this, and I don't feel like I fully grokked it. So, yeah, I would love for you to
Yeah.
just go over it again.
If you didn't fully grok the connection, you're thinking exactly right, because this part is unsolved yet. And that was sort of my call to arms, right? So here we
Okay.
know on the left side, like this is the, maybe within whatever noise or like small perturbations, that is the optimum network for XOR. That's been shown 1,000 times in academic circles. On the right, in instance-based learning, that's been shown as the optimum data collection to represent an XOR system. And what I find fascinating is if you look at the number of aggregations and the number of connections, the rough compute, yes, I'm kind of hand waving because what goes on in a neuron versus what goes on in your interpolation, yes, they're mathematically a little bit different, but zooming back out, they're of similar computational complexity for the same underlying problem. And additionally, the one on the right is, like, I can understand that. I can put those data in. I can, in a half a sheet of paper with pencil and paper, work through and convince a professor or whatever, a colleague, this is exactly how I got the answer with the units of measurement. The one on the left is much harder to do that, much more opaque, but it has different types of efficiencies. So the part of the open question here is, if we drill and zoom into just this, it's a toy problem, but it's sufficiently challenging that I really like it. Can we make these direct linkages from this subset of data? And even, looking at, how much data do you need to learn XOR? That itself is an interesting question. I don't know that that is solved. Because if you just have 4 data points, is that noise? Or is there actually signal there? Versus as you get more and more data points from a Bayesian perspective, if every data point lines up with one of these 4 and you've got 4 million data points, of course that's the right answer. The same way that if you got 2 data points, is it a line or is it a really squiggly mess? And that's the underlying function, you don't know. But I think that this is a toy problem that, obviously, even in the early days of grokking, of scaling up deep inference, the XOR problem and similar problems were used as some of those core research problems. I think it is applicable here. I don't know if it's as applicable, but I still think it's applicable, especially with like actively learning. Like, you've got this XOR problem. How many iterations back and forth do you need to go? How much data do you need to get the fact that it is an XOR and get a right answer? But then kind of how efficient is it, and how, can you characterize that uncertainty well? So I just like this as one toy problem to try to unify these.
Got it. And the diagram in the bottom left, can you walk me through that one?
Oh, sure. That's just a small neural network of, you have x1 and x2, the 2 different axes. So basically, what is the position and what is the color of it? Basically it's a 3-dimensional data set, right? X-axis, Y-axis. Is it positive? Is it negative? And then so each of those are the links of the neurons. Basically the output of the when this neuron activates, it puts forth a positive signal or a negative signal, and these are just the aggregations there. So it's a, basically it's a two-layer system. The X1 and X2, that's the inputs. So then you've got the other two, the layers in the middle. I think I spoke wrong before and I said there's three, but those left two are just the inputs. So you got 3 nodes, but you have 6 connections there.
Great, thank you.
So I guess you could make a Bayesian. Sorry for repeating myself, but I guess you could make a Bayesian. Like, so I suppose in this task you basically get samples on this 2-dimensional space, and you have to group them, and you have to learn that the top right and the bottom left are the same category. Is that right?
Yes.
So
that's right. Yeah.
So I guess you could. That reminds me of some structure learning things, right? Where you have to find out that there are in fact 4, let's say, Gaussian or Laplace distributions here, and 2 of them come together, and the other 2 go together, and you have to learn that structure. So whatever, that's what my intuition is when I see this picture, to go to a Bayesian structure learning approach. There are some within active inference that indeed do use usually Gaussians, although I'm happy to.
Yeah, so two thoughts on that. One is that just like the universal approximation theorem for neural networks, there is a similar equivalent theorem, but it's a little bit weaker for KNN, k-nearest neighbors in S-based learning, which states that regardless of your distance function, as the amount of data goes to infinity, your learner, well, that goes to infinity, but as it grows, the error rate, the Bayesian error rate, goes and must be under a certain amount. And you can calculate that. It's a very pessimistic proof, but it shows that as it goes to infinity, you converge to the right answer no matter what. So it's kind of the KNN equivalent of the universal approximation theorem. And then from the Laplace distribution, some of Nassim Taleb's work saying, if only Carl Friedrich Gauss was not such a force of personality, and we didn't care so much about differentiability. Laplace distribution is more robust because the mean absolute deviation, it's faster to compute, and information theory tells us that they're both equivalent. So if you know the mean and you know the mean absolute deviation, the maximum entropy distribution is singularly the Laplace distribution. If you know the mean and the variance or the standard deviation, then it's the normal distribution. But it depends on what you know for a fact about the world. And there's a lot of good things about the Gaussian distribution as well. I tend to bash on it, but I'm very emboldened from an information theory and a physics perspective that maybe Laplace is the right way. And think about, if you have a lot of data, sure, you can say, well, there's additive relationships here. So central limit theorem, this will be a normally distributed, marginal distribution or whatever. But if you zoom in really, really tight and you only have 10 data points, what can you really say? So you could compute the variance or the standard deviation, but as you zoom in, the mean absolute deviation is more robust. Now, if your data actually has a Gaussian distribution, well, central limit theorem, as you add all these Laplace together, you'll still get the Gaussian distribution on the other side. So there's really no loss in generality, and an increase in robustness, and an increase in computation. And I do wonder at what level are there any equivalents? Maybe it's very deep in the quantum level, and it doesn't really matter that much for biology, or maybe there's some biological mechanisms that are closer to that hat distribution as opposed to normal, but we're just seeing the sum of all of them. We haven't drilled into that yet. Maybe. I don't know.
Interesting. So that's on a kind of a very technical, specific discussion, but that's interesting. I'm used to using Gaussians everywhere, as you can sense. So that's always nice to have your mind opened a little bit. I see Ron has a question. Then I have one more question, which is a small one. But I also just want to make sure that if others in the audience have, yes, and I see David has a question. So let's say Ron, David. One more from me if there's time, and then it's Carl's turn, I think.
Yeah, I'm going to ask a question which is counterintuitive, and I don't know if this is the right audience, or the audience will appreciate it, and perhaps I'm not articulating it well, but I'm just thinking through, like, okay, XOR, we only have 4 data points, right? And from my understanding of the XOR paper was it showed you couldn't use the linear line, and so you had this, okay, a perceptron cannot achieve this, so now we're going to introduce these hidden layers, right? And I mentioned this, Chris, because you talked about complexity. And I was like, okay, yes, we could introduce the hidden layers, or we could just have a deterministic rule. to say like if you do that right. And so which is actually less complex and in which situation would you use that? And then, we throw in beliefs. And so now we're throwing more complex math, right? There's all these different ways to structure it. I'm just wondering, when we brought up the phrase of structure learning, is there a governor of like, oh, here is far less complexity if we just use a hard-coded rule. Here is better because we have 10 million data points. So yeah, we might actually want to use some, other type of math. That's the part that's missing for me because developers are making conscious decisions, and forgive my lack of expertise in data science, right? So there's the softmax versus the one versus rest, right? A single perceptron. Okay, so I just as an experiment, I created a perceptron for each class and then a deterministic rule. I don't, you get over the XOR problem just in a very different way. What is the field, or I don't know what to call it, that is determining, given this task, yes, we should use probabilistic methods, or no, we should use deterministic methods? Is that neurosymbolic rules? Or I just don't know the language. I'm sorry. I'm trying to learn from you all. So thank you.
I'm really glad you asked that question because that was something I was going to totally gloss over and actually rewinds into my past. So my training is game theory and information theory. Machine learning was something I sort of picked up in grad school and didn't like because I couldn't understand how it worked. And then I sort of backed into it. And the thing that I was working on immediately prior to this was something known as evolutionary feature synthesis. So it's a domain of evolutionary programming. So if you think about like, evolutionary mechanisms oftentimes take different configurations and do different types of fold, different types of blending together of those. Evolutionary programming is taking programs, graphs, and doing the same sort of thing to them. Now, if you remember back, especially in the like when Tim Berners-Lee was pushing really hard in the semantic web, and there was that big like all the big AI conferences, like AAAI would be like, well, these are the stats people and machine learning people, these are the symbolic people, and they were like, they might as well have almost been two different conferences other than a little bit of cross-pollination. And then everyone's like, oh, well, the machine learning people won. Well, not entirely, right? Like we still want to have these efficient mechanisms, and that's why we're using, with LLMs, we're having them generate code and run that code because we can't rely on them. As these large neural networks learn, there's these grokking, these little mechanisms, these functions that are sort of crystallizing, just like you have water and it freezes. There's these little areas that freeze, and like it built a function that does a thing. It learned how to add, but it might have taken a lot of data. So for example, if you estimate the number of math problems that a professional engineer with a certification has done in his or her life, it's probably in the order of 50,000 to 100,000 math problems, but they're using paper and they're putting on their mind, all the pieces they're not doing in their head. Versus an LLM, the smallest training sets, like the one from DeepMind on GitHub from like 5 years ago, is like 16 or what was it, like 6 million problems. Like that's just to learn the basic math, right? So there's a very different thing here that we're using all this data to make these systems grok quickly to build these mental models, but there's got to be a better way. And me working in evolutionary feature synthesis, I didn't even know it was called that when I was working on it with the genetic programming techniques, was trying to evolve like what is an efficient function that fits this, and just let it evolve and mix these things the same way you would have crossovers and what have you. And sometimes it's able to do remarkably well, but it's really slow to learn. But the thing you get on the other side is something tight that can be computed in nanoseconds, and is very efficient. And my thought through a lot of this, and this is more going to the speculative side, is that instead of using these large neural networks to build and crystallize these little things that we don't know what they are, like what functions has it really learned? Yeah, they're universally applicable. Can we instead couple these data-driven techniques with evolutionary feature synthesis, or things that we know? This is Newtonian physics, right? So if that's the case, just use the math. We can put that in some part of the model, and instead of having to learn both like, does this data correspond to a Newtonian physics problem, and build a model in the learner for Newtonian physics, why can't I just learn, well, this is Newtonian physics, this is a ground truth that we have solved as humans, and just learn that mapping? Now it's exponentially less amount of data that you need to learn the same thing. And I wonder, where the techniques that people use for LLMs are let's grok and build these things with a lot of data. Using the principles of active inference and some of the things that we've worked on, could we learn those and decouple those independently in different subpieces so that we can apply evolutionary feature synthesis on this, going back to that generalization problem on this piece. And now we can really compress this down and have tight models that are human understandable, and then have that mapping there and really have the best of both worlds. So instead of having an LLM generate code that gets in run, that's super inefficient. Can we bring these two worlds together? So Ron, to your point of, how are these things coupled? When should you use a function versus when should you use data? I don't think it's the symbolic people versus the machine learners. We've got to come together, but can we make that even tighter of a coupling?
Yeah. I'll just add briefly that the active inference route would usually be Bayesian model comparison approach, right? Where you can compare your you could in principle compare your Newtonian mechanics model to your big one and use Bayesian inference to select between them, right? But if you can calculate the model evidence, but and there are open-ended versions
even to
of
that
these
point. Kolmogorov complexity and measuring that complexity of those submodels, like Bayesian information criterion or AIC, like those sorts of things, like those you can apply pretty natively to some of this. And you start to say like, well, let's not solve it because Kolmogorov complexity is undecidable. Let's just treat it as an empirical problem. I think you're absolutely right. I think we can measure some Bayesian inference on some of those models, even if they're symbolic.
So I see David has a few points more.
Yeah, so and I think Chris got to where I was raising, which was when we were talking about whether or not Laplace or Gaussian, I would actually say this is where Chris interactions with the world teach you which distribution is better. And so it actually doesn't have to be decided if you're in a world in which power laws are favored versus Gaussian, then but that also gets to the point that I think that the challenge with the current approach to LLMs, aside from the fact that they don't really build true world building models, is I think the way you solve the XOR problem is you are approaching it with whatever axioms you have developed about the world. And if you have none, then 4 data points is insufficient. I mean, that's the reality. But if you have some axioms that say the roulette wheel when I spin it, or whatever whatever phenomenon you're looking at 4 data points are, then you can apply that. And so I think, while I recognize that the 80s and 90s with rule-based systems collapsed underneath their weight because rules by themselves cannot explain everything, I think we're also realizing the limit of unstructured data by itself without the ability to generalize some rules also is suboptimal. And so I look forward to when some rules can either be expressly given by the creators of the system or inferred through mechanisms by the system itself.
100% agree. And even to your point on the Gaussian versus Laplace, like in our code, we have a preprocessor macro that says, do I want to use Laplace or Gaussian? And we can flip it. And it takes about 3 to 4 times more.
You could easily create a world in which the central limit theorem does not exist and the universe does not converge. And that would be very
but the point here is that it doesn't matter. It takes 3 to 4 times longer to compute, but the results we see are statistically almost indistinguishable because as you zoom in, you can reconstruct either distribution. It's just the Laplace primitive to reconstruct the Gaussian distribution is more efficient computationally.
So I'm just keeping time in mind a little bit, but I just wanted to. So one thing is that this also, you said in the beginning that it was a model-free method you're using, right? And the active inference approaches are usually model-based, although with some structure learning, they become kind of partly model-based, partly so the model structure is created as you go, kind of, and that's I think that's one frontier currently in the field is how do you do proper structure learning in active inference? So someone like Lancelot da Costa is specializing specifically in this, and well, that might be an interesting field. That's not my specialty, so I'm useless. but
so point to that is I say that are we model free? I say the data is the model. So if you want to partition, let's say you think in the world of policy versus world, or maybe you think in some other way, it's a data partition problem, not a model partition problem. That's kind of how our framework and our theory approaches it.
Maybe similar to the active inference and neuroscience generally notion of attention. So that's different from attention heads in LLMs, but in the sense of picking what data I should care about and what I shouldn't, and learning that I should go.
Thanks for making that connection. So, think about what does an attention mechanism do? It sort of looks back in the context, and given all of the things, increase and decrease the probability of influence, oftentimes with harsh cutoffs of what I'm looking at. We actually can do the same thing. So by changing that deviation, we have something we call dynamic deviations. So we can sample based on the relevant data. What should that uncertainty be? We can condition everything for a problem. So what is the probability that a feature is important to this particular set of data? We actually compute that on the fly based on conditional probability. And so we mimic I wouldn't say 100% of what attention mechanisms do yet, but we're getting close. But we mimic largely what attention does purely in information theory / Bayesian inference.
Yeah, that's interesting. So from a Bayesian perspective, it's often a task of learning the precision, or noise of a given channel, like essentially how a given set of data, how relevant it is for the inferential target, right? And that's a Bayesian learning process of its own.
This is the flip where we say the uncertainty is so wide, like as it increases, this gets washed out.
Yeah.
So it's the same result, but the inverse of mechanism.
Exciting. I'll mention, but not ask, but I'll just mention that one other place where I thought there was probably something that active inference could also get from some of the work you're doing is you're mentioning the Pareto frontier, where one of the things that can make active inference slow in the context of machine learning, so that doesn't matter so much in when you model people's behavior and brains, but if you the computational load matters if you're in artificial intelligence, is that the action selection part for active inference is technically to go through every policy. So that's every combination of actions a certain of time into the future. And then you run your predictions forward and you make a predictive posterior depending on every combination of actions. And then you calculate the expected free energy and you pick the action that minimizes this. And it does not take many possible actions and minutes for this to explode quite quickly. So people have different tree search methods that essentially do not look at every option, but tries to prune that quickly branching tree of options. And that sounded similar to me. Yeah.
Yes. And one thing that we've done that we often do with our customers is instead of trying to reason through all of the trees and do a tree search, we just sample from the posterior distributions and sort of leverage out here's 30 or 100 possible futures that are most likely given what you're trying to optimize for and the dynamics of the system and the dynamics of state. And we're able to come up with those distributions. Now, of course, it's not going to be as robust as a tree structure, especially if you're applying, you're going from MCTS to Monte Carlo regret minimization. Of course, there's a night and day there from a game theory perspective, but still, that's an area that I'd love to push more into as well, especially for adversarial play. But even from an MCTS perspective, I think we're kind of sampling and doing, it's not MCTS, but it rhymes a little bit if you squint and look back.
Exciting. Okay, so I'll end with a brief, just a different kind of question, because I'm certain that if someone had time, they could spend time on finding formal points of kind of connection between your work, active inference, maybe also James March's work in cybernetics, and I imagine there would be plenty of people interested in this for sure. And I guess one thing is formal points of similarity and dissimilarity. Another one is where is it useful or what can you do from the other one and so on. But of course that requires someone to do this. So I guess the question is, are you considering? Many people, Carl will maybe also have some thoughts on this, but of course many people do not necessarily have the bandwidth to take on that as a side project. So maybe I'm just asking, kind of pragmatically speaking, are you looking for a collaborator who would be interested enough in the work you do to kind of do a teamwork, or would one have a PhD student? Or
we're, like I said, we're a for-profit commercial entity, but we do have open source, the core pieces of our math are open source on our GitHub. So if you want to play with it, you could go pip install Howso engine right now and be up and running in less than 5 minutes. And I think some of the aspects of reinforcement learning and data distillation, we've got some recipes up there to play with. So I think that the barrier of entry is just basically learning our software and learning our math. But from a practical perspective, of course, I'm interested in how can we get better results. But from an academic perspective, I really care about the theory as well. Now, obviously, wearing many hats, I've got to juggle between the two, between the different things. But happy to chat with anyone who's interested in this sort of area.
Yeah, okay. Okay, so maybe we can consider this, Carl. Maybe I can think about if I know people who would maybe be interested. So, I would in principle be interested, but I promised myself to be careful with taking on new projects this year. Just started a new position, although I'd be happy to hear more because this is very interesting. Okay, because I guess one option is to hire a PhD student or a postdoc who has training in one field and has time to learn the other field so that they can write about the connections and so on. But yeah, okay.
Yeah, and I'd like to thank David Bray for introducing me to this. So being the information theorist and game theorist, was working in this field for a while, and we're getting results. Like, I'm going to keep working on this regardless. But then when David Bray's like, about active inference, I'm like, yeah, I heard about it. He's like, you should look closer at it. This a few years ago, it looked like, oh, whoa, this is like, there's something really here.
Okay, very exciting. So in the interest of time, I'll give everyone just a last option for a last question or comment. And if no one raises their hand, then I do think it's your turn, Carl.
Good. Is it my turn now?
Yes, indeed.
You have the floor.
No, that was a wonderful presentation, and also a wonderful discussion. So, so many things to talk about. I'll start with, I liked your log table story. Exactly the same thing happened to me when I was 10 years of age. My father brought in a slide rule and locked the door and said, figure it out, and left me alone for 3 hours. That's how I got to understand the beauty of logarithms and the like, a very formative experience. You've covered an enormous amount of ground and done it with an exuberance which is untypical for these presentations, so congratulations on that. There are lots of things that it would be nice to talk about. Many of the things you talked about are a little bit outside my comfort zone, but there are a number of sort of foundational issues which I did recognize. So I think the most useful thing, just speaking to what's happening now? Just speaking to Peter's last question, if there are interesting leads that in your sort of when you're not actually working for the company at the weekends, you may or may not want to follow up, then I think it would be our job just to sort of highlight them. They may be false leads, but they may be useful leads. So I'm going to try and focus on things that are currently the foci of work in the active inference space and the free energy principle that you implicitly spoke to. So things like that sort of hierarchical pyramid of structures and the like, and some people might call sort of causal discovery just from the data. So I'm going to sort of focus on that. It does indeed touch upon the other way of looking at this, which is structure learning or Bayesian model selection. And Bayesian model selection here, just interestingly, is exactly the same as natural selection and evolutionary algorithms. It's just you're replacing the fitness function with the free energy functional. So I think all these things are intimately related. So I'm just sort of framing what I'm going to do, which is go through a series of papers that may or may not be interesting. I'd say some of them might be false leads because I don't know the literature deeply, but some of them might sort of just pick up on your intuitions or aspirations in a way which will give you a bit more motivation for pursuing that angle as opposed to an alternative angle. Before I do that, I'll grab the screen in a moment, largely because the papers will enable me to remember all the things that should be said. Before I go through those, though, I just wanted to pick up on some of the conversations, particularly with David and Ron. So let me just to remind myself, I'm going to share my screen now in the fond hope that that all works comfortably. Yeah, the last where is it now? Yes, it was, yes, that discussion about XOR and David's point that if you have in mind some putative explanations, models, hypotheses, causal cause effect structures that could be brought to the table to best explain these sparse data, then it is now a relatively straightforward problem to minimize the surprisal of these sparse data conditioned upon a small hypothesis space or a small set of numbers. And I think that's absolutely right, and I think that's the sort of key to one of the challenges that I see being presented in the machine learning community, which is moving beyond current generative AI into the world of system two type thinking and artificial reasoning. Reasoning, what's the best explanation for these sparse data? And of course, that's exemplified by the ARC3 challenge. Have you come across the ARC3 challenge?
I've heard of it, but I'm not super familiar with it. It
Right.
rings a bell.
Yeah, it's something that I noticed you said twice you are a for-profit. There's a little bit of money to be made if you can win the ARC3 challenge. I think it's $1 million US. It's not an enormous amount, but it would certainly be, if one could find the right technology to solve what cannot be hacked with transformer architectures or deep RL, then you can, the ARC3 challenge is exactly there to showcase this different way of doing things, and it's really a statement that the machine learning community are looking for the next big thing. Given what you've said, I think that the next big you view the next big thing exactly along the lines that you've been talking about in terms of sort of maximum applying basic principles of sense making and the physics of information processing to that include the maximum entropy principle, Occam's principle, and making the most of small data. So this paper is one, the active inference approach to this. It's under consideration now at a peer-reviewed journal, but it has been released on archive. So I just put this up here as, if you like, a generalization of the XOR problem when you've only got 4 data points. So it is solvable, but you have to be you have to have in mind solutions, very much like your mathematician solving her 50,000 problems on paper. And I think that's the secret sauce to the next, the next kind of artificial intelligence. And I repeat, Lancelot da Costa, who is a gentleman who is focusing on structure learning, is the second author of this paper. He's worked with people like Josh Tenenbaum and Yoshua Bengio and the like, or has done sabbaticals with them. We're considering related issues. The other two things I'm going to delete. Sorry, I know that this is being recorded, or I assume it's being recorded. So I'm putting these up so that you can come back to it, because I appreciate you've been standing there now for several hours. So I'll speak quickly in the knowledge that if you wanted to follow this up, you can come back to the recording and pick up this from archive. The other sort of generic issue that both emerged in your that's the same thing, in your presentation and in the subsequent discussions. I'm thinking here about this sort of notion that if I got a measure of surprisal and I make a move and my surprisal differs from what I predicted my surprisal would be, I know that it's time to revise or do something different. I think that's the sort of key issue which David was also speaking to, and it really does emerge as a key aspect in the active inference field at a number of different levels. At a sort of broader level, many years ago, we're talking sort of well over a decade ago now, the surprisal as measured by the variational free energy or negative elbow in machine learning was used to create an ontology of emotions. So if the free energy was going down, that basically means that, well, if the elbow or the surprisal was going down, that means things are behaving much as you expected, and you feel good about that. But if it's going up, then you feel bad. And then you set that against the level of overall surprise. Is the world predictable or not predictable? And then you have a phase portrait of surprisal and its rate of change as you accumulate more data. And this was used.
Fascinating.
This was used as in fact, these people who have now left the field, but this, I think, this person was a theorist from behavioral macroeconomics. But they wrote this paper framing all emotions or valenced characterization of states of being, or particularly sort of information processing and surprisal minimization in terms of the free energy principle. And then he elaborated this really very interesting. So you can replace F with your surprisal here, and then you've got all sorts of ways of describing how your machine is currently feeling, simply based upon these phase portraits with higher order temporal derivatives of surprisal. So I thought you might quite like that.
We need to quantify that. That would be really maybe low-hanging fruit and exciting.
Yes, yeah, and there's no reason why you couldn't do that if you've actually got the measures of surprisal at hand. The other place that this several years later was fully endorsed was in a particular kind of surprisal, and this was expected surprisal. In my world, it's called expected free energy, and it underwrites the policy selection. So I can't remember who said it, but one of you were talking about, if I've got a number of policies, paths into the future, I can evaluate the expected surprisal and then score the goodness of each of these policies or paths into the future in terms of the expected surprise, or the expectation of the surprisal under some predicted posterior over the outcomes, the observations of the data. And if one does that, and does that in the context of variational Bayes, which is effectively active inference, and then look at the mismatch between the expected surprise that you anticipated before enacting your policy and what happens after you enacted it, the difference behaves exactly the same as dopamine in the brain. So dopamine is one of those sort of love or sort of emotional neurochemicals, neuromodulators. But if you simulate it, then as soon as you resolve uncertainty, or as soon as the surprisal is behaving in a way which is consistent with what you thought would happen as you roll out into the future, then you get these bursts of dopamine and you feel very, very good. So again, this takes the sort of emotional phenotyping and evaluation of your belief updating right into the world of planning and using your surprisal measures as the basis of predicting the future, and specifically different paths into the future that are conditioned upon certain policies or certain ways of sampling data. And this also applies to the epistemic imperatives, or the maximum information gain kind of policies, the exploratory policies. So if you resolve your uncertainty and you click on this news feed, or you access this social media and resolve some uncertainty about some unknown, then you can simulate these bursts of dopamine, which of course are one of the cornerstones of the neurobiological formulations of reinforcement learning and the like. So I thought you'd like that. Well, both you and David would like that sort of neurobiological and indeed emotional vindication of what you were talking about. So just coming back now to sort of ways of selling the surprisal minimization. And before I sort of pick up on ways of potentially interesting leads for you, or ways of selling it to, say, an academic community such as ours, it strikes me that what you're bringing to the table is effectively has some specifics to it, but generically it is effectively a likelihood model free way of doing inference, and in particular a likelihood free or likelihood model free way of doing inference, which acknowledges the potential utility of using Laplace distributions densities as opposed to Gaussian densities. And I know that's a bit technical, but it was something that you kept coming back to, so I think it's just worth acknowledging in this summary. And certainly like Peter, as a physicist, I am committed completely to Gaussian via exactly as you say, central limit theorem. So as soon as you start dealing with a Langevin equation or any sort of Fokker-Planck formalism, you're almost inevitably dealing with Gaussian, with one exception, which I think licenses your focus on the Laplace, which is not the computational ease, but the fact you've got this sort of implicit non-Gaussian heavy-tailed structure that is an emergent property when you do get scale-free structures. Say, for example, under the renormalization group. So I suspect the reason that your Laplace works so well, one reason why it might be an apt thing to choose is not so much just because it's really fast to compute, but because it's got in it the ability to accommodate the the self-similarity or heavy-tailed correlations and distributions that you get in real-world biotic scale invariant systems, where when you're moving from one scale to the next, then suddenly you can't rely upon central limit theorem in the usual way. So I'm just making that point just to acknowledge that I think there's a really interesting space. It did remind me of also of Geoffrey Hinton's SMP clustering analysis, which has become very popular. Again, just relying upon heavy-tailed distributions or assumptions about the the information geometry of distances in some space, in your instance, observation space. But now, just sort of how you might sell this to other audiences if you had time to. I think it is interesting just to note the mathematical equivalence between surprisal, the negative log probability of some data under conditioned upon the process or a model of that process, should you want to articulate it, generating those data or measurements, and the surprisal we sometimes is called surprise, and which is bound by the variational free energy, and in Bayesian statistics, model evidence. So as you're minimizing surprisal, you are maximizing model evidence, or more simply maximizing evidence on the marginal likelihood. And philosophers love that because it means they can write books about things self-evidencing. And in fact, Jacob Howie has now written a book literally within the past few weeks. I think it's just come out, pursuing exactly this marginal likelihood maximizing, surprisal minimizing imperative for existence, and interpreting this in terms of basically we're all in the job of gathering evidence for minimizing the surprisal of our sensory exchanges with the world. So he's called it the self-evidencing agent, mind existence and predictive processing. So it would be, I think, compelling if you could just tell people that surprisal, self-information, marginal likelihood, evidence are all the same thing, and you can tell all sorts of different stories depending upon your favorite interpretation. Have you come across likelihood-free Bayesian inference?
I'm not sure that I have. That seems new.
Right, good. Okay, so this is probably one of the most promising leads for you then. I'm going to give you a much less promising lead in a second, but I think this is going to be the most promising lead for you. So likelihood-free or likelihood model-free Bayesian inference, I think is probably the closest thing, or the simplest route, should you want to join the dots between what you have been describing and a Bayesian formulation that has under the hood or behind the scenes some implicit model, but you never actually have to go there. You can just work in data space. And because you're just working in data space, you never ever have to specify the likelihood model, which means effectively you're likelihood free. So if you imagine the likelihood model, the probability of some data given its latent causes as the likelihood, then if you don't need to refer or to model or to invert an explicit generative model with latent causes, then you free yourself from having to work with the likelihood model, and implicitly now you are you can do everything in data space or measurement space, and I think that's basically your gift. That's basically your position. So the equivalent, I think, but I don't know. Again, this is slightly outside my comfort zone, but I think it's a lead which you may or may not want to pursue. The equivalent approach in Bayesian inference would be called likelihood-free Bayesian inference, and there are a number of applications of this. It's quite a big thing in both public health and epidemiology, and also in molecular genetics and genomics. Sometimes um, called approximate Bayesian computation, ABC. Now, approximate Bayesian computation is a synonym for these likelihood-free Bayesian inference approaches, not to be confused with approximate Bayesian inference, which is variational inference with an explicit generative model, where you do have to build an explicit generative model of latent states that could be of Gaussian or Laplace distributions, but crucially, they are latent states that have its likelihood mapping to the measurement in and of itself. So it might be useful just to do this is not a, I haven't read this paper. I just picked it up as a recent sort of survey. No, not this is not a paper. This is actually an illustration of its application to public health and epidemiological modelling by the UK government. Just picking up on the utility of these things. But you can, I'm sure, if you go to Wikipedia or to the specialist literature and just look for likelihood-free Bayesian inference, I think that's probably the easiest route if you wanted to join the dots. There's another thing which that may be a false lead, and that's the work of Bengio and subsequent colleagues on equilibrium propagation. And I'm not sure, because I don't really know how this works, but I had some of Joshua Bengio's students presented in this meeting once, and I remember coming away thinking, that's just likelihood-free Bayesian inference. So it may be that some more recent work of Bengio's group in Montreal is pursuing a related theme if it has this likelihood-free aspect or model-free aspect that you are celebrating. And in particular, the two things converge in causal discovery, which you were talking about slightly later on, trying to fill in find which data will fill in the gaps to elucidate cause-effect structures, even if you haven't got the cause-effect mapping. If you've got the consequences of a cause-effect mapping, then you should be able to recover or discover the underlying causal discovery. So causal discovery is basically Bengio's group's way of talking about structure learning with just given data. And they've been looking at sort of something called G-flow nets. So these are more appropriate for sort of dynamics and transition dynamics and sort of paths on graphs as you move from one state to another state. But they could also be relevant for equivalent flows on data. And indeed, I think they try to configure it purely as G flows on data, but I may be wrong. So this could be a false lead, but if it's not, it might be an interesting lead from your point of view. I repeat, sort of very much sort of celebrating or focused on Joshua Bengio's work and his group's work. So they may be useful leads, or they may not be. I don't know. Yeah, we've done all those. Very good. So this I think is going to be a useful lead, and it speaks directly to your modular carving nature at its joints by composing the effective modeling of sparse data in this pyramidal or hierarchical fashion that you showed with a nice graphic, and also hinted at it in the last question on your last slide about what is the link between the recursive modeling of data and hierarchical generative models in the brain, or cortical hierarchies, for example. And I think the answer is very much as Peter was intimating, lies in abstracting cause-effect structure from data in this recursive, scale-free fashion. And that has certainly been a hot topic of interest in my field, not so much in the biomimetic, but in the applied artificial intelligence space. Again, featuring people like Lance da Costa. So this paper has been published in Entropy, and I'd recommend you actually read more of the abstract of this one, because it may have some stuff in here which you might find useful. And as Peter intimated, it's an example where you're basically building models, but you're building them from the ground up, like de novo learning. So you're starting with the data, and then you're taking abstractions of the data to create new data, usually of a compressed sort. But there being a close relationship between compression, maximum entropy, and minimum description length, and maximum marginal likelihood, and you do it recursively. And you can cast that recursive operation in terms of the renormalization group, which just brings us back to the scale-free aspect, which brings us back to the Laplace distribution. So this I thought would be a useful read for you, because it applies it to in this sort of it's not model free, because the explicit agenda is to build a generative model, but you're actually building it bottom up. Exactly as David was saying, as opposed to sort of starting top down. You're just basically harvesting data in a way that conforms to the maximum entropy principle, um, under minimal constraints, just looking at the sort of correlation structures or spin block structures, if you're a physicist, of the data itself in terms of the neighborhood relationships or the information geometry of neighborhoods, for example. So I don't know, but I suspect that you would immediately see the utility of this kind of approach, and possibly um, um, be able to reframe it in terms of exactly what you have been doing, and thereby provide another link. What I wanted to do, though, so it goes through with the sort of classic MNIST-like classification problems in machine learning, and then goes on to dynamics and sound file, or no, movie. So you can do the same thing with movies and then sound files, and then ultimately goes to the optimization of state action policies using a very simple example, using an arcade game. Speaking to the Peter's question about how do you get action in here? Just open brackets, it strikes me at the moment that you're dealing with state action policy optimization when you talk about the sort of cart pearl problem, or the sort of mountain car problem. So these are a special case of state action policy optimization that in principle, I'm sure you could, not trivially, but in a relatively straightforward way, solve, because there exists a mapping between data and the best kind of response, and you can put a transformer architecture in there between them should you want to, or you can put your architecture in between and do it much more quickly. That should not be confused with sequential policy optimization. I think you're going to be in a different world after you've solved the state action policy optimization. So sequential policy optimization actually requires you to have roll out into the future under counterfactuals, and you have to do planning. So that's where the expected surprise comes in, or the expected free energy, just to sort of situate your benchmarks and selling what you can do in terms of working from state action policy optimization through then to more difficult sequential policy optimization issues. I think this one just deals with the state action policy optimization by playing a little arcade game, but you should get the sense of how you demonstrate to people how you can deploy the same architecture and technology to tackle increasingly important problems. I wanted to. Oh, sorry. Yeah, this is not for you. It's for other people watching the recording. Just to unpack your comments about Gaussian process modeling. And certainly, you know, in in my world, the 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 importance of having um, a statistical or information theoretic model or probabilistic model of how data lie in relation to each other is extremely important. Sorry, when I say my world, in this instance, I'm talking about my role in brain mapping and making statistical sense of images. So here, the dependency between, say, voxel values in a brain scan becomes extremely important. And I was smiling when you talked about the Minkowski because we used to use that in terms of differential geometry and topology, and what we used to call them, the Euler characteristic. That was a good one as well. So we actually used to use those in sort of use random field theory in order to interpret, and still do in fact interpret sort of brain imaging data. But as you say, they're also quite important in terms of providing a mathematical calculus to articulate probabilistically the relationship between data points in some space. It struck me you should now invent Laplacian process models and sell that. That's what you should do. That'll make you famous. So that's that. That was just an introduction. Just finally to join, you repeatedly talked about this is just a sort of an overview paper of a narrative kind that may or may not be useful if you wanted to cite the foundational fundamental links between surprisal minimization under these Laplace-Gaussian process models. Laplace process models. And Bayesian mechanics are celebrated in the free energy principle and active inference. And you mentioned several times the maximum entropy principle. There is a duality between the free energy principle that leads to the Bayesian mechanics that could be a reformulation of your surprisal minimization in terms of the maximum entropy principle due to James, but also the maximum caliber principle when you're looking about little paths, particularly into the future. That becomes particularly interesting, in terms of path integral formulation, which I'll just mention next. So most of the primary literature in that area has been written by a chap called Dalton. So he's got a few standalone archive papers just showing the relationship between the surprisal minimizing process and the maximum entropy and maximum caliber principles of James that themselves inherit to a certain extent from the Prigoghine's sort of theory of dissipative structures and minimum entropy production principles, which themselves are one take on the cybernetics that David was talking about. So I think there's a really interesting opportunity here to join all the dots together, should you have time at the weekends. But specifically, just to sort of demystify some of those relationships, this is a formal treatment of the information geometry and the Bayesian mechanics of the free energy principle, which, when applied to behavior, gives you active inference. But I've just put this up here just because it's got, I'm hoping, the sort of key equations. Damn it, no, sorry, I deleted the one I wanted to show you. Never mind. We can just I can just make the key points here. If you regard surprisal and the variational free energy as synonymous, which you can when you're not trying to model a system, but you're trying to describe a system. So you just assume that the system is its own generative model. Then the surprisal and the free energy become the same thing. So a free energy minimizing process, namely active inference, that's an example of predictive coding if you ignore action. And surprisal minimization becomes synonymous. And that's nice because that entails entropy maximization, because the free energy is just the energy constraint afforded by the constraints on the kind of thing, the kind of system, or the kind of data cause effect structure that you're dealing with, minus the entropy. So as you're minimizing the free energy or minimizing surprisal, you are implicitly maximizing an entropy of sorts. This entropy is a measurement entropy. It's not the entropy of the observations. It's an entropy of the belief structure or the subpersonal probability distribution over what you think caused the observations. So in my world, I really liked your sort of physics of measurement sort of perspective. But in my world, you have to be quite careful between the difference between an observation and a measurement. So an observation is a real variable, so a bit of data, whereas the measurement is the inference about what you think caused that. So measurement now becomes inference. So I think what James was talking about was actually the entropy of the measurement. It was how things are actually measured, and that you get just by unpacking and basically just unpacking by inflating the expression for the negative log probability just by adding and subtracting two other terms that include this sort of measurement distribution, and then rearranging them in terms of a constrained entropy maximization process. So I think there's a really deep and simple connection between the way that you're articulating things and how the free energy principle would treat this. This is interesting. The structure of this free energy or surprisal is interesting. Now, I haven't done this, but I would imagine that you should be able to project this entire system onto the measurement space and then minimize the free energy in measurement space. And I think that's what maximum likelihood free Bayesian inference does. So basically, instead of trying to optimize a probability distribution over the latent causes that would require an explicit generative model, you now project the causes through your likelihood model into observation space, and then just optimize your free energy in observation space, which means you don't need to worry about the latent causes. So I think that the likelihood model free approach that is committed to doing everything in data space can be derived simply by projecting all the latents here, eta, through some putative likelihood mapping to observation space, and the whole thing now is articulated in observation space. And I think then the Laplace assumptions about the correlation structures or the information geometry in observation space, you could reverse engineer that and talk about your implicit generative model, but you don't need to if you can get the functional form of the free energy or the surprisal out in data space. So I suspect that's the simplest way to sort of connect active inference of the free energy principle to model free or likelihood free approaches that you're talking about. The other reason I just wanted to show you these equations is that you can take the functional form on these different, just for your interest. I mean, I'm sure, well, I'm not sure you know this, but for those people who don't know this, you can rearrange this sort of inflated expression of the surprisal or the negative log of self-information to express it in terms of what a statistician would like, which is complexity and accuracy, which is where complexity is just the difference between before you made your measurement and after you made your measurement. It's the difference between the implicit sort of realistic beliefs or the measurement probability that you get, and you want to try and minimize that. So coming back to this notion that if the world is, if I measure the world and I'm not surprised, then I've got a good model of that world, and the degree to which I have to change my mind to accommodate these new data scores the complexity cost of accommodating accurately or explaining accurately these new data. So generally I want to either change my mind or change the priors, and that would be the structure learning part of it, changing the prior belief about how my data were generated. And then in machine learning, just rearrange these terms and it becomes an upper bound on the surprisal. So this is the negative log likelihood of the join of the sensory data S here. So this is your surprisal without worrying about this divergence term, which is 0 in this particular instance. But the same functional form roughly appears when you take a look at the expected surprisal or the expected free energy when you talk about the future. So you take an expectation over the posterior predicted density over outcomes in the future, and then that complexity becomes risk, and the accuracy or the negative accuracy becomes ambiguity. And these are the sort of concepts that people in control theory and economics talk about when they're choosing a good policy or investment policy, or in control theory, what I'm going to do next. And again, you can rearrange these in terms of the expected surprisal, which could be read now as an negative expected cost. But the that bound, that KL bound that you get with the elbow in machine learning, now becomes an expected information gain, which speaks to what your conversation with Peter about how to comply with the principles of optimum Bayesian design. If it is costly to get the next bit of data, what data point should I choose in order to resolve the most uncertainty about the statistical dependencies that underwrite my data? And that can be scored with a KL divergence between the sort of before, with and without the observation conditioned upon here my action or alpha. So this would be one way, not the only way, but one way of formalizing this imperative to resolve uncertainty, or to pick carefully the right kind of data that will maximize your sample efficiency in generating a good probabilistic description of the nature of the data or the process that you're dealing with. But this only really applies, say, practically when you start to now pick a small number of policies of the kind that you were talking about with Peter. But at some point, it might be an interesting extension once you've gone beyond cart pole balancing and the like to actual sequential policy optimization. This has this sort of, to my mind, probably more important foraging, epistemic, uncertainty reducing, information gain, infotaxis aspect to behavior, which I think is the key thing that underwrites the sample efficiency, which I suspect your approach will provide, probably already is providing, over conventional machine learning approaches. Good, and that's it. That's all I have to say. Thank you for inspiring me.
That was awesome. If I could give 2 really quick reactions on things you said. I didn't talk much about bandwidth selection or dynamic bandwidth selection, but you touched on it. And basically, as you get more and more data, at some point, because it's surprisal, the tails fall off very rapidly, and we just truncate it, and it's sparse and efficient. And then also, we're measuring approximations of the Hausdorff dimension for like how much data should we use to cluster? Like what is the clustering topology in that dimensionality? And going back to the scale-free analogy, thinking like, well, we're beings in basically 3D space, but we're kind of 4D in terms of our internal structures. There's a similar thing in the clustering. And as we zoom in again, the Laplace assumption of the local, even finding the expected value with 15 data points that are relevant, the central limit theorem already starts to show its head, so it starts to look Gaussian. So but then also we can capture the long tail. So I think it's really blurring those worlds in a very interesting way. And the second thing I wanted to react to was your comment on, I believe it was dopamine, and looking like I expected this and I observed this. An interesting thing we see in industry with our techniques are sometimes customers ask us, can you explain what happened in our model that's already deployed? And I say, we can give you a justification, but we can't necessarily explain it. So by, in parallel, inferring what we would have predicted, and then saying, given the answer of this other model, here's what it would have predicted. Not only can we tell, obviously the difference there, but we can tell, given the explanation, the inductive bias-free things that led to that decision, we can measure the difference there and what's the KL divergence of the predictive qualities of both of the explanations, and see, is there an underlying conceptual drift in addition to the data drift? So I think that maybe with that dopamine reinforcement, like maybe there's some interesting research there. And I also wanted to thank you for a lot of those papers. Some of those look very interesting, and I plan to read those.
Excellent. Yeah, so you can that KL divergence as dopamine is very closely related to reward prediction errors in neurobiology, which was a really hot thing for the past 20 years. So that's another nice story that you could tell in that respect. Absolutely.
Yeah.
Then I think there's nothing left except for me just to briefly round off as we do normally. So Chris, if anything comes up, do reach out and maybe I can be of help. And for sure, I'll send you the recording of this link, or of this meeting at least. And so apart from that, we just want to thank you for the presentation and give you one last round of applause. And indeed, thanks for the inspiration. Have a pleasant.
It's been a great pleasure.
For us too.
Thank you.
Have a good evening or afternoon, depending on the time of day.
Thank you.
Good evening. Good day.